Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from NEC Labs. We have Srihari Cadambi. He is a senior researcher. Hari, welcome to the show today.
Thank you, Rich. Good to be here.
Well, it's great to have you on the show. You know, Hari, you and I met at Supercomputing, and you told me a few things about this Cosmic project. So the way I understand it, Cosmic is it's a middleware for Xeon Phi, but what it does is scheduling and resource allocation.
Yes, it is. So we're going to talk a little bit more about the Cosmic project and then how it evolved from a research project into what's almost a product now.
Okay, so it's just a project at this point, not a product?
Right. So it began as a research idea at NEC Labs about a year and a half ago. And then subsequently, it's been adopted by our business units in Japan. And it's right now in what we call a pre-commercialization phase. So we are actively looking for beta customers. And then once we find some, it will be productized officially.
Okay. So I brought your slides up, Hari. Why don't we learn some more?
Okay, fantastic. So today I'm going to be talking a little bit about Cosmic, which, as you said, Rich, is a middleware specifically for Xeon Phi servers and clusters. And this is work that began at NEC Labs America. We are in Princeton, New Jersey, and we collaborate with our business units in NEC Japan. So before I talk about Cosmic, let me give you a little bit of a background. I'm sure most of this community knows the Xeon Phi, which was launched by Intel back in 2012. So the Xeon Phi is basically an x86 coprocessor with more than 60 cores. It works together with a multi-core like the Xeon, for example, and is connected over the PCI bus. Now, the nice things about the Xeon Phi coprocessor, which is relevant for a middleware like Cosmic, is that A, it supports a parallel programming model that's familiar to a lot of people like OpenMP, and B, and this is of particular relevance to us, is that it runs Linux. And running Linux allows nice features like multiprocessing, memory management, and swapping and stuff like that. And as we'll see in a second, that's going to be very germane to this talk. And given that it's a highly parallel coprocessor, it's good for many scientific applications, especially in HPC. So in slide 3, we see that because of these nice features of the Xeon Phi, it's seen a fairly fast ramp up. There's many hardware vendors, including NEC, that offers Xeon Phi servers, and there's many clusters that's been commissioned already, including some very high performance ones. The top 500, the number one, I believe, is a Xeon Phi based supercomputer, the fastest supercomputer in the world today. And NEC also offers a Xeon Phi server, which is shown on the right-hand side of slide 3 here. And it's our Express series. It's a fairly compact 1U form factor with, it's pretty densely packed inside, has 2 of the Xeon Phi coprocessors with some advanced features. And one particular differentiating factor that I'll talk about is the middleware Cosmic. Before we dive into the middleware, let me step back a little bit again and talk about how Xeon Phi clusters are managed today and what the problem is with these management techniques. So there's a lot of third-party managers, cluster managers, which work with the Xeon Phi clusters, and most of them follow what's called an exclusive allocation policy. And what this means is that a single Xeon Phi device is dedicated to one user until his or her job completes. So there's a figure below on this slide which shows a 4-node cluster, which means there's 4 servers, and each server has one Xeon Phi. This is just for example purposes. And there's 2 users. There's Amy with the purple shirt on the left-hand side, and there's Charlie with the brown suit on the right-hand side. So Amy needs, one Xeon Phi for her program, and Charlie needs 3 Xeon Phi. So between the 2 of them, they've occupied the entire cluster. And if another user, if you go a step forward, you'll see Bob coming in, and he needs 1 Xeon Phi for his program. Now, given this policy of exclusive allocation that's exercised by the cluster manager, Bob has to wait until either Amy or Charlie have completed their jobs so that he can run his program. So this is sort of a conservative policy, slide 5, and one would ask, why do cluster managers follow this sort of a policy? So it has some obvious advantages, the biggest one being that it avoids complications resulting from resource oversubscription. So let's take a quick look at what resource oversubscription is and how Cosmic solves it. So in slide 6, we show this by example. So say Amy and Bob, 2 users, each want to run a program or a job that uses a single Xeon Phi device intermittently. And this is the coprocessor offload model. Now the question is, do they each need a device exclusively, or can they share a single Xeon Phi device? So on the left-hand side, you see Amy's program that's shown in using yellow rectangles. So it starts, and then it goes on to the Xeon Phi, comes back to the host, and it goes back to the Xeon Phi, and then ends. And on the right-hand side, you see Bob's program, which begins, uses the host, and then is offloaded to the Xeon Phi, and then comes back to the host. Now, the question is, can these 2 programs, if they run like this, can they share a single Xeon Phi? So moving forward, there's 2 problems that are caused by sharing, which is why most cluster managers do not do this. The first problem is the programs together can oversubscribe the hardware threads, which we call thread oversubscription. And what this means is that, let's say Amy's program needs 160 threads on the Phi, and then Bob's program also needs 160 threads. So together, if they were to share the device, they would need 320 threads, which is more than what's available even on a mini-core like the Xeon Phi, because the mini-core supports 240 threads in hardware. So this thread oversubscription is okay for multi-cores, but because of the expensive context switch in a mini-core, we have measured the slowdown to be 2 to 3x. And having a 3x slowdown because of sharing is unacceptable. You might as well just run the 2 programs sequentially. So that's the first problem. The next slide shows the second problem, which is memory oversubscription. And in some sense, this is even more catastrophic. So let's say Amy's program needs 5 gigabytes of memory, and Bob's program needs another 5. So together, they need 10 gigabytes, which is more than the physical memory on the Xeon Phi. It's usually 8 gigabytes, going up to 16, of course. But the point is, if the programs that share the Phi need more memory than what's physically available, then randomly programs can crash. This is because of the Linux's out-of-memory OOM, or killer, as some people call it, which terminates certain processes when the physical memory is oversubscribed. And this could be catastrophic. So we don't want this. So I guess sharing is bad from this point of view. So the next slide sort of summarizes this. So why do we need the conservative policy? Because we avoid resource oversubscription, we avoid thread and memory oversubscription. It is safe, there's no crashes, easier management. But there's some problems with this, and this is where Cosmic comes in. In slide 10, we see the biggest downside of this conservative policy, and that is poorly utilized Xeon Phi coprocessors. What the chart shows you is our measurement for some typical workloads of the core utilization on the coprocessor. So on the x-axis, you see time. On the y-axis, you see the core utilization. And although there are peaks which go up to like 70%, you can see sort of the average that hovers around 40%. Now, what this means is that only 40% of the cores in the coprocessor are actually doing useful work. And this is because of the intermittent use, non-sharing policy, and so on. And this kind of sounds bad. So what does low utilization actually mean? The next slide shows you the biggest effect of this thing. So if the coprocessors are very poorly utilized, one may need to provision a larger cluster than necessary to get the same quality of service metrics, like to support the same number of users, to get the same turnaround time, etc. And having a huge cluster can get expensive because of capital cost, power, maintenance, administration, and so on. And the other downside, and the big downside of a conservative policy, which is shown in slide 12, is that users have to wait, and this can actually result in annoyed users. For example, if a user has a short job, like a 5-minute job or a 10-minute program, and if somebody has occupied the entire cluster with a 24-hour program, the user with the short job actually has to wait, and doesn't seem like a fair policy. So this is where Cosmic comes in, and slide 13 shows you Cosmic from sort of a 50,000-foot view. So Cosmic is a middleware that allows safe Xeon Phi sharing. Now on the right-hand side, you see at the bottom, you see the hardware. You see the host processor, which runs Linux, and then you see the coprocessor, which runs Linux with the drivers together called MPSS. And on the top, you see the applications. So Cosmic is something that fits in the middle. It is completely transparent to the applications and is also completely invisible to the underlying system software like Linux and MPSS. And what it does is it transparently discovers an application's resource requirements and schedules jobs such that they can maximally and safely share a Xeon Phi. So the users who run applications don't even know Cosmic's running. And underlying system software like Linux and MPSS do not need to change in any way, shape, or form because Cosmic has been introduced. So in slide 14, we show the benefit of Cosmic using the same simple example. You have Amy's program and you have Bob's program. Now in the middle, you see what Cosmic does. It basically intersperses the Xeon Phi portions. So once Amy's Xeon Phi portion is done, Bob's Xeon Phi portion is moved into the device. So in other words, neither user has to wait for the other's program to completely finish before starting his or her program. And because we have device sharing, users do not have to wait. Utilization improves, and hopefully the overall performance also improves because the user doesn't have to wait. And we'll see the numbers very shortly. Now, before we talk about the numbers, very quickly in slide 15, we show what Cosmic does in terms of resolving user directives. So one problem that could happen if two users share the Xeon Phi is that whenever users use many cores, sometimes they affinitize their threads to the core. So for example, they can say, I want these threads to run on cores 0 through 30 or something like that. Now, these directives could potentially conflict if two users are simultaneously on the same device. Now, what Cosmic does is it transparently intercepts these directives, and it spreads the load within the device. So it balances the load and resolves conflicts. So users never use the same cores. They use other vacant cores as and when available. In slide 16, we show the improved utilization with Cosmic. That's what we have measured and published. The blue line shows the older utilization, which averaged around 40%, and the black line shows the utilization with Cosmic, and that bumps it up to more than 70%, which means that earlier only about 40% of the cores were doing useful work on average, and then with Cosmic it goes up to 70%. In slide 17, we show some performance benefits. Now, this Cosmic actually improves performance in some cases, and this is primarily because users do not have to wait, and sometimes these wait times can be long. So because users do not have to wait, it does improve performance. So average latency goes up significantly. The make span, in this case, we have 64 jobs on a single server. The make span improves, and the code utilization, of course, improves in this case as well. And we also have a demonstration, which I believe you might have seen at Supercomputing. But let me very briefly go through the demonstration. That's in slide 18. So this demonstration shows an application which is image segmentation. In one case, it's running without Cosmic on a Xeon Phi. In the other case, it's running with Cosmic. In both cases, we have 6 users all running image segmentation on each of the devices. So let me just play this the video of this demo, which was shown live. So on the left-hand side, you see the images being segmented without Cosmic, running on one Xeon Phi. So the left-hand side starts off first because you don't have any sort of overheads of Cosmic, but very quickly you see the right-hand side complete all 6 images. And basically what's happening here is that on the right-hand side, the 6 users are allowed to go simultaneously, and Cosmic manages the sharing on a single device. On the left-hand side, the users go sequentially. And so overall, it takes longer. And the performance improvement has been measured to be 2x. In this case, you see 1.8, but it depends on the specific data set. It's 1.8 to 2.5x faster with Cosmic. And again, this is completely transparent to the applications and the system software. So moving ahead, Cosmic, so what we briefly talked about was Cosmic on individual servers, but certainly the application for a middleware like this is actually on Xeon Phi clusters. And Cosmic is very easy to use on clusters. It's easy to interface this with third-party cluster software like Torque or Condor, Altair, PBS, and so on. The only thing that changes really is the cluster management policy. So the third-party software basically can now say that we do not have to have this exclusive allocation policy because Cosmic is going to take care of sharing. And we have also gone ahead and built a special cluster component, which is shown in slide 19, the light green box on the left-hand side. And this cluster component is an optional component which further improves utilization using some intelligent algorithms. And what we have measured is with the Cosmic cluster component using Condor, we can reduce the cluster footprint by about 50%. Specifically, what that means is you can get the same make span with a 50% smaller cluster because of sharing. So slide 20 summarizes the presentation. So at this point, as I mentioned, Cosmic is in a pre-commercialization phase, and we are ready to engage with beta customers. So to determine if somebody could find Cosmic beneficial or not, these are the main questions that they could ask. If they manage Xeon Phi servers or clusters, and if they use off-the-shelf cluster management software, especially with exclusive allocation policies. Now, if these two things are true, then they will likely benefit from Cosmic because we improve Xeon Phi utilization by sharing in a completely transparent way, both to users and to the underlying system software. And it's easy to add on to third-party cluster tools. And finally, how interested people can get more information. Please contact us. There's email addresses both for the research labs and our business units in Japan. We do come on site and make presentations and demonstrations and show how Cosmic can be used. And if anybody is interested in evaluating Cosmic, please just ask. We will be happy to offer evaluation with support. And finally, there's more information as well as demonstrations online at this site. And with that, I'll conclude my presentation. Thank you.
Well, thanks for that, Hari. A question is, I know it's in beta, but how disruptive is it to bring Cosmic into an existing cluster environment? Say I had something like Condor as my resource manager.
Right. So we believe it's not disruptive at all. We, in fact, have deployed Cosmic with Condor for our cluster experiments. And in most cases, Condor doesn't have to be modified at all. So we want to try to make Cosmic as transparent as possible. And hopefully, we wouldn't need to change anything inside Condor or Torque or any of these third-party cluster tools. The only thing that needs to change, perhaps, is the policy that these third-party cluster tools follow, such as exclusive allocation policy. So because if Cosmic is there, they could relax that policy. So we envision this to be not disruptive in terms of users not having to change their applications or third-party cluster tools not having to change at all.
Yeah. And I'm curious, Hari, about the origins of this. I mean, you guys have a Xeon Phi server product, as you said. Were your customers coming back to you and asking, why is the efficiency so low when I cluster these together, or how did it start?
That's a good question. Actually, it started because one of the customers that NEC Japan has had a potential candidate which they wanted accelerated on the Xeon Phi, but in that particular application had multiple processes, And each process had very few threads, but the important thing for them was throughput. So what our collaborators in Japan were investigating was how could we have all these processes um, on a single Xeon Phi device and still provide an improvement in the throughput. And then we came across this oversubscription problem, because when you have multiple processes, that's kind of like having multiple users competing for a single device, because a process's memory could grow and the process could, suddenly request more threads and so on. So we came across these oversubscription problems at that point because of this particular customer's application. And that was how Cosmic began. So, and then we took these oversubscription problems, and then we saw that other people, for example, GPU clusters have reported utilization issues as well. So we sort of put the two things together and made that into a research project, and happily that evolved into something that the business units liked. And so here we are.
Yeah, yeah, and so you brought up GPUs, which was my next question. I mean, I would guess that GPUs might have a similar problem in clusters, or would that be a different kind of implementation?
Right. So we haven't actually looked at GPUs from this particular standpoint. They certainly have utilization problems. One difference is that we use Linux facilities quite a bit in order to get these benefits, and GPUs do not run Linux. So it's a little different from that point of view. And the other difference is that GPUs perhaps may not have the same issues in terms of thread oversubscription, because they do have hardware support to support many warps with many threads. It's a little bit different in the Xeon Phi. So I would say that conceptually, in terms of the utilization, these concepts would be applicable to GPUs as well. But in terms of the actual implementation and where Cosmic is, it is somewhat specific to the Xeon Phi.
Yeah, yeah. Well, looking forward, then, we've seen some announcements of that Knight's Landing is going to come out next year, and that's I guess it's a bootable version of the Xeon Phi. Would this implementation, would it lend itself to that, or would that be something you have to look at when it comes?
That's a good question. We have discussed the Knight's Landing a little bit internally, and we think one of the facets of Cosmic, especially the Cosmic cluster, would be very applicable in the Knight's Landing, the bootable Knight's Landing. And this is something that I didn't mention it, but we do have another publication that's coming up in IPDPS, which describes that technology. And we think some of that could certainly be applicable for the Knight's Landing. But I guess since it's something that we haven't done and it's part of our roadmap, I can't say too many things about it with certainty, because we don't know which way it's going to go. But certainly the Knight's Landing is very exciting, and we think that's a big opportunity for Cosmic.
Well, great. Well, Hari, this has been very interesting, and I'd like to thank you once again for coming on the show today.
Great. Thank you very much, Rich. Great being here.
You bet. You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.